Welcome. So today I'm going to show you a tangible application of complex numbers, and this is aimed for all of you engineers out there. So the first thing I want to remind you of is that e to the theta I is cos theta plus I sine theta. Okay, and so this is what we're going to use, where I is the square root of -1. Now let's consider a differential equation, second order, so y double dash minus 2y dash plus 2y equals 0. So this is homogeneous second order linear. So remember what we do with this. We say the characteristic equation is lambda squared minus 2 lambda plus 2 equals 0. And so I've just copied the coefficients from here. I've gotten the powers from how many times this is differentiated. So solving this requires using the quadratic formula because it's not so clear to see how you might factorize this. Of course you can do it, but it's not so clear to see it. So lambda equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay, and so let's simplify this. We have 2 plus or minus the square root of 4 minus 8 is minus 4 over 2. Now inside the square root we have a negative number, so we need to introduce the letter I, the square root of -1. So 4 is 2 squared, so we can pull out the 2. And so we have 2 plus or minus 2i all over 2. Now this is 1 plus or minus I, because we can divide the 2 into that 2 and into that 2. All right, so moving on, let's label these. Lambda 1 is 1 plus I, and lambda 2 1 minus I. And now remember what you did when you solved second order homogeneous equations when both of the lambda were real number. Here they're not both real numbers. But when they were both real numbers, you set y of x equal to a constant a, e to the power of lambda 1 times x plus b, e to the power of lambda 2 times x. Okay, so we want to do this here, but these two numbers, they're not real numbers. We can sub them in anyway, so let's see what we get when we do that. Okay, so here we're going to sub in these two complex numbers. So we have y of x is a e to the 1 plus I in brackets x plus b e to the 1 minus I in brackets x. Now remember, we've got an expansion we can do there, and then we can use an exponent rule. So we have e a to the x plus ix, b e to the x minus ix. All right, now there's an exponent rule that says we can break this up. So we have e to the x, e to the ix, and similarly over on this side, we have this. Now, e to the x is common in both, so let's factorize that out to the left of this expression. So e to the x, a, e to the ix, b, e to the minus ix. Okay, so we've got this. This is our y of x so far. But there in the exponent, we have a complex number. So what we want to do now is use this result on e to the ix. And so we have y of x is e to the x times a in brackets cos x plus I sine of x. And then we have plus b times cos of minus x plus I sine of minus x. Okay, now cos of x is the same as cos of minus x. So cos of minus x is cos of x. And now sine of minus x is the same as minus sine of x. Okay, so now at this point, let's collect like terms, collecting in terms of cos and sine. So we have e to the x, a plus b times cos of x. And then we have b, hang on, this should be an a, shouldn't it? That should be an a up there. We've expanded across there, so that should be an a. So then we have a minus b times I times sine of x. Okay, and now at this point, we can give a plus b a new name. Let's call that c1, and we can give a minus b times I a new name. Let's call that c2. So then what we have is y of x is e to the x brackets c1 cos of x plus c2 sine of x. Okay, and so complex numbers were the intermediate step in getting this. Now notice what we have up here. We have 1 times x. That's the real part of 1 plus I. And then we have another 1 there. That's the absolute value of the imaginary part of 1 plus I in there. And so our general formula when we have complex numbers is y of x equals e times the real part of alpha times x, c1 cos of the absolute value of the imaginary part of alpha times x, plus c2 sine of the imaginary part of alpha times x.